Here's the thing, x and y do not have to depend on each other directly. They can both depend on something else entirely, something we usually call t, and we're going to watch that happen right now as a curve draws itself out. That something else, t, could be time, could be an angle, could be anything. The point is that x and y are each just watching change and tracing out their own path as a result. Some curves simply refuse to be written as y equals a function of x. Think of a full circle or any curve that loops back on itself. A single x value there would need to map to more than one y value, and a function is not allowed to do that. Introducing a parameter, t solves this problem completely. Instead of forcing y to depend on x directly, we let both x and y trace out as t changes, as if t were a clock ticking forward. Here is a concrete example. Let x equal cosine t and y equal sine t. As t sweeps from 0 up to 2 pi, watch the point trace out a complete circle. Let's tilt the camera and look at that same circle from a light 3D angle, just to see the shape of the trace more clearly before we go back to flat 2D. Why does this trace a circle? Because that is exactly how sine and cosine are defined in the first place, as the x and y coordinates of a point moving around the unit circle. So plotting cosine t against sine t can only ever give you points on that circle. Now let's convert this back into a direct relationship between x and y by eliminating the parameter t. We start from the definition, x equals cosine t, y equals sin t. We use the identity cosine squared t plus sine squared t equals 1. Substituting x for cosine t and y for sine t, straight into that identity gives us x squared plus y squared equals 1. So the parameter t has completely disappeared, and we are left with a direct equation in x and y alone, which you should recognize as a circle of radius 1 centered at the origin. This works because t was only ever an intermediate stand-in. Anything you can solve for, you can substitute out. Now for differentiating a parametric curve, the rule is dy by dx equals dy by dt, divided by dx by dt. Why does this work? It comes straight from the chain rule. Dy by dx equals dy by dt times dt by dx, and dt by dx is just 1 divided by dx by dt, so the t's link up and cancel through the chain, leaving that clean division. Let's use a worked example. Take x equals t squared and y equals t cubed. First, differentiate each with respect to t on its own. Dx by dt equals 2t and dy by dt equals 3t squared. Now divide dy by dx equals 3t squared divided by 2t, which simplifies to 3t divided by 2. To find the gradient at a specific point, let's use t equals 2. Substituting in, gradient equals 3 times 2 divided by 2, which equals 3. So at that point on the curve, the gradient is exactly 3. And we never had to convert back to Cartesian form to get it. Let's lock in the full process, one step at a time, in the exact order you'd actually use it. Step 1. Write x and y each as separate functions of a parameter t. Step 2. To trace or sketch the curve, plug in values of t across the given range. Step 3. To convert to Cartesian form, eliminate t using an identity or direct substitution. Step 4. To differentiate, find dx by dt and dy by dt separately. Step 5. Divide dy by dt by dx by dt to get dy by dx. Step 6. Substitute in a specific t value if you need the gradient at a particular point. Watch out for this common mistake. Do not divide dy by dx by dt, and do not flip the fraction the wrong way round. It is always dy by dt on top, divided by dx by dt on the bottom. Here is the simplified version. X and y both depend on a parameter t instead of on each other. Eliminating t gives you back a direct x-y relationship, and the gradient is always dy by dt, divided by dx by dt, thanks to the chain rule.